Live? Yeah. Good morning, everyone. What a pleasure to be here. My name is Bruno Santos. I'm an associate professor here at TU Delft, but more important today, I'm here to present the ReMAP project. So I'm also the coordinator of the ReMAP project. And today we are here with pleasure. And I mentioned not me, but also my colleagues that who took part of this project. We are here with pleasure to show you our results, which we are very proud of. And also because we don't want to have a communication in one direction, also to hear from you what is your experience, what is your vision for setting CBM as a common practice in aviation. Okay, so welcome very much. Let me say also good afternoon and good evening for those ones that are following us online, maybe from other regions of the globe. The presentation, please. Yes, okay, so what I'm going to do before I give the floor to the ones that are going to present some more details of the results is to give you an overview of the project. I presume that most of you are here, you know a little bit about the project, but still to start and everyone to be at the same page, I would like to tell you what was the goal of our project. So our idea was to develop an integrated fleet management solution. That the goal was to improve the way that we do aircraft maintenance by following an adaptive condition-based maintenance strategy. And that was our goal. And we did that together as a consortium. I must share with you that I had perhaps the easiest task as coordinator because we never had issues as a consortium. Everyone was engaged. Every partner here contributed in a way that was expected, in most of the cases beyond what was expected. So it was an excellent project also in that regard. How do we see maintenance taking place in our approach? So this is perhaps nothing new for you if you have followed CBM, but the way we see it is a cyclus. So we have aircraft flying with sensors, airborne sensors. We use those, the data from those sensors we collect, and we use that to train and to use on machine learning algorithms that then are going to give us information about the condition, health condition of our systems and structures, but also about the future conditions, expected future degradation of those systems and structures. So that's diagnostics and prognostics. If we have this information, including all the information that we have about the maintenance program, then we can define and optimize the maintenance schedule. And by doing that, we help the execution of the plan. If we do it that adaptively, meaning that we use information as it comes and adapt our plans as fast as possible, keeping the coherence of the plan, then we facilitate the maintenance execution. Maintenance execution takes place, aircraft flies, more data, more better trained algorithms, and so forth and so on. And that's the way that we see it, the cycles. And to answer our goal and follow this approach, we have developed multiple technology blocks. So we look into an open IT platform, which will be presented by Miguel in the following presentation. We have also looking into data-driven methods for structures, aircraft structures, running lab tests to collect data and simulate the uses and fatigue of these structures, and then developing our prognostics and diagnostic algorithms. We also look into data-driven methods for systems and look into a concept of physics model for systems to help us to better analyze the root cause of failures. And then we put all together in a machine learning algorithm, reinforcement learning algorithm to update and produce maintenance schedules as the information arrives to us. And this is what we put it as being the integrated fleet health management solution. And to analyze what this would mean, we looked also in terms of reliability and efficiency and in terms of what could be the impact in the future of adopting this approach. And this actually answers one of the objectives of our project. So what I'm going to share with you now in a nutshell is share with you the objectives that we have for the project and how we achieve them. The project is is over in the end of August, so we are concluding the last tasks, but most of the objectives, of course, they have been achieved. So let me share this with you. So the first one was to develop this integrated approach. This is what we have been doing in the last years. Then the second one was to explore and optimize use of different sensing technologies. And what we did was to equip 48 coupons, which were tested, but were sensorized with piezoelectric sensors or elements, optical fiber optics, acoustic sensors, and also the software around the sensors were developed. We also looked into an hybrid method, combining two of these sensing technologies to better analyze the damage of the structure. We look into the reliability of these sensors in different conditions, how they will degrade. And finally, but not least, we also developed a proof of concept of what could be a self-diagnostic method, which went beyond what we had ambition in the beginning. Actually, this picture here is from, I believe, from the hybrid solution that colleagues developed. The third objective was to develop an IT ecosystem of cloud of service, of models that could support the flow of data and the flow of decisions during this process. And I'm not going to extend too much about what we did. As I said, Miguel is going to present that. But we observed consulting partners and other entities that one of the challenges was to have more data, because luckily in an airline or air transport industry, there are few failures, few incidents. So we need more data to really train our methods. So we understood that we had to involve more than one airline, but then there is the problem of sharing data. So we came up with a hub and spoke architecture that can allow the federation of airlines or nodes here, and the solutions, the methods are in the core and are shared by airlines. This has been deployed, validated, and it's currently running at KLM. Further objective was to develop a data-driven probabilistic algorithms for aerostructures, both for damage monitoring and remaining useful life estimation. So we develop, as probably most of you know, in terms of structural health monitoring, there are almost no sensors in the aircraft, so we developed this in the lab. And we test these 48 coupons that I mentioned before with more than 30 million fatigue cycles. And we developed these diagnostic and prognostic algorithms that we're going to hear from Theo in a couple of minutes or in 1 hour or so. And we also developed something that is very important and I'd like to highlight, is an open source database of all these tests that can be used by anyone, including manufacturers or operators as a reference, or algorithms developers as their own database. The fifth objective was to develop an hybrid approach for systems. And there we develop many different PHM algorithms with multiple machine learning techniques for different systems. We looked at 10 aircraft systems from 3 aircraft types during this project. Also looking at user interface. So one of the things that we took particular attention is that going from our algorithms results to something that the user can make use of it, we need to better display our results. So we also work on some user interface solutions. And as I said, we looked into a concept of physics-based model to help to improve the root cause analysis. We also look into a possibility of having lean algorithms running on board and helping already during the flight to have a solution that can help the pilots or the team on the ground to already identify what could be a problem. So we consider the edge solutions, which were tested in a laboratory environment, of course, not in an aircraft. And their colleagues use something that we don't use only for this edge condition, also for the other solution for PHM. The colleagues looked into federated analytics, so trying to use information from multiple aircraft at the same time to enhance the quality of the algorithms in each one of the aircraft. Objective 7 was to develop an efficient maintenance packaging and scaling optimization. And we use a reinforcement learning there, also combined with the dynamic scaling algorithms to, as I said, dynamically adapt the plan and provide a solution, a consistent solution at all time with new information. So we look into scaling maintenance checks, but mainly we look into rescaling allocation of tasks as they come to the ongoing maintenance plans. And we make use of the results from the PHM and SHM, so from the prognosis for systems and for structures, to estimate when we should maintain those systems or structures as information comes. The structure was not implemented, I must say. We only look into systems, but the same path could have been followed for structures. And we develop a prototype of user interface, again, to help the user to understand what we are doing there and the schedule and adapt the schedule according to the needs of the user. Objective 8 was to look into safety risk, safety risk assessment of the methodology that we were proposing. So in that regard, we develop an agent-based model to represent the maintenance process and to assess what would be the efficiency and the reliability of our methods. And we started by interviewing several stakeholders and identifying the hazard associated with condition-based maintenance and also deployment of machine learning or AI solutions. And finally, but not least, by running simulations, what colleagues did was to look at these maintenance strategies and compare condition-based maintenance with our current strategy or different levels of health monitoring being adopted in a maintenance practice, and compare multiple solutions. Finally, we also look into improve root cause analysis of failures to facilitate future structures and systems design. We are still concluding this objective, but as I said, first we look into a concept of physics, physics models, digital twins to help us also to understand better the degradation of structures and degradation of the condition of systems. And for instance, colleagues from the structural part of the project, they estimate that there is a potential of primary structures from our aircraft to have a weight reduction of 10% if we follow condition-based maintenance. There were also practical goals, and with this I'll finish our goals. So of course we wanted to quantify the impact of what we are doing, so we developed multiple solutions while developing the methods, also scenarios of what will be the future if we extend this from our 10 systems to eventually 100 systems. So we made those analyses, again, also in terms of reliability, comparing the multiple strategies. So we developed a multiple analysis on our solutions. We also validate these technologies. So for systems, PHM, and for scaling, together with IT platform, these algorithms are running at KLM as a kind of shadow tool, so we can analyze and understand what will mean in practice. It's running, it's feasible, it's doable, it's there. So we are very happy to, that we achieved that. And finally, there is this goal of involving partners in this discussion, in defining a roadmap or defining next steps, because ReMAP project is eventually just the start of something larger than what we had before ReMAP, but it's not the end of something. We did that in different ways. Unfortunately, we were hit, like all of you in different ways, we were hit by COVID, so we had to change our plans. So before COVID, we engaged in some fairs. After COVID, what we did was to use online platforms to communicate. And today, I'm very happy that we are here. And eventually, we see also again tomorrow and Wednesday for the International CBM conference. This is the agenda for today. So after I stopped, I'll give the floor to my colleague Miguel to look into the IT or present the IT ecosystem. We'll follow then the multiple, let's say, blocks of our projects. My idea is that at the end of the presentation, there will be eventually 2-3 minutes for any clarification question. But then, in principle, we won't have time for really a discussion, so let's leave it for the coffee breaks for sure. But there will be half an hour from noon to 12:30, where we can have a Q&A about the whole project and we can discuss it. But as I said, after lunch, we want to reverse the room. So not that I want to ask the ReMAP partners to shut up, but I want to listen to other stakeholders, people that were not directly involved in the project, to also share their opinion in terms of technology for PHM and SHM, but in the first panel. And in the second panel, to look into the deployment of CBM conditions. We invite 3 colleagues for each one of the panels to be here with us, but that doesn't mean that we are only these 3 colleagues that will be here, just a way of starting discussion. And we also involve people online if they have questions. House rules, engage in discussion, that's why we are here. We want to hear from you, we want to discuss what we achieve. As I said, in the morning, clarification questions at the end of the presentations, but technical discussion will be before lunch. In the afternoon, everyone is welcome to share the ideas. Colleagues joining us online, use the chat functionality to ask questions. We'll try to answer at least some of the questions. If we have time, we'll answer all. We are recording these. The cameras, you can see the cameras. If you have any problem with the image, please avoid yourself to crossing the cameras or let us know. We'll try to remove that footage when we share the video from today. And that's it. So I'll give the floor to my colleague Miguel. Yeah.
Thank you, Bruno. So, as you mentioned, I will be making the presentation for the IT platform. So, my name is Miguel Ángel Esbrí, and I am representing Atos, who is the main technological partner who was in charge of implementing such a platform. I cannot see the presentation. Okay. Okay, so as Bruno mentioned also, the main goal of this IT platform was the main idea behind was to develop a collaborative IT platform where the airlines could bring their data and in an efficient manner to analyze it and carry out some diagnosis and prognosis algorithms on the data in order to understand if there were any problems with the components in the aircraft. The idea was also to do it in a very efficient manner and in a secure environment. Okay, the first idea that we had was to, we said we have the cloud, so we could put everything there. So we put all the airlines data sets together with the machine learning algorithms developed by the machine learning developers, and also with all the maintenance plans and so on. But the fact is that we realized that although collaboration is a key thing in the project, the reality is that the airlines are not keen on sharing their data because obvious reasons, because this could impact their own business if other competitors could access to this data. Also, the data from the airlines, they require different levels of anonymization in case they put this data in a common repository. And also, they were very preoccupied on the traceability of the data. So they wanted to know who was using the data and for which purposes, which was not easy to solve. So at the end, the implementation that we did, and we think that solved mainly all the problems that we found, was that, okay, we are still using a cloud environment, but each airline has its own node, and we will see this later on, where they store the data, so it's only accessible by them. And on the other side, we have the modelers who develop their algorithms, and they put it in the main infrastructure of the IT platform, so they can be used by the airlines. And what we have also done is to develop a common data model. So this makes life much easier for the machine learning developers, because what we realize is that each airline has its own data, but the data from, even if it's the same component, it may have different naming for the parameters. And okay, for the developers, it was much easier if they have a common framework where they could use the same parameters for developing the machine learning algorithms. Also, what we have done is to do or to implement an open API and SDK, so it's very easy for the machine learning developers and the airlines to integrate the data in the platform, so they don't have to develop new systems in order to ingest the data. And we have also implemented security and audit mechanisms, so we can know who has done what and who has run each algorithm in each of the nodes. And it's also an implementation that allows to run different machine learning algorithms implemented with different techniques on the background. So as I mentioned before, we have two main components. One would be what we call the platform core or hub. So this core is the one in charge of making the federation of the different airlines nodes with the main component. So that gives access to the airlines nodes to all the algorithms that are deployed in the main core by the developers. This federation is made in a secure manner, so not anyone can register its own node. So this has a manual procedure where we register each airline, and once this is done, they have access to all the capabilities of the core. It's also, this core module is the central point where the machine learning developers access to understand which is the data without accessing to it directly offered by the airlines, and then they are able to develop their own algorithms and then offer it to them. And yeah, the idea is that also in the future, other third-party application developers or companies can also develop additional functionalities on top of this core model. On the other hand, we have the spokes or the node module, which are run by the airline companies. So as I said, this is hosted internally in the IT platform of each of the airlines. So that makes that no other one can access to their own data. So it's kept secure and safe. The node also allows to the airline to define the different roles and users within its own organization who will be able to access to this data. And an important thing is that the node allows to automate the ingestion and transformation of all the aircraft sensed data or collected from the sensors into this common data model that ReMAP has defined. So afterwards, the different machine learning algorithms can be run on top of the data. Also, the node, when the machine learning developer is trying to develop a new algorithm for a specific component, as we said, they don't have direct access to the data, but they have an insight on which are the parameters that they can use to make their own model. So what the system offers is that the modeler develops an algorithm. This algorithm is transferred locally to the airline infrastructure and is run, and some result is produced. And then this result is sent back to the developer so he can analyze if the algorithm is complying with the required parameters to see if the algorithm is good enough for the results expected. Well, in this image, you can see in a beta diagram what I have been trying to explain. So we have the ReMAP core, which is run by Atos nowadays, and it's the central point where the machine learning developers can understand which is the data available, and also we have a catalog with all the different components that you could find in the aircrafts. So all those components have their own specific parameters that can be used and later on used by the machine learning modelers. On the other hand, we have the airline node, and the first step in order to be able to run all the system is that the airline federates with the core. Once this is done, the airline has access to the catalog of the components together with the machine learning models developed by the developers. What you can see on top of the airline node is all the different data sources that can be ingested into the platform. So, of course, we have the sensor data coming from the aircrafts, but the airlines have also information about the different maintenance plans and schedules for the staff that could make that maintenance. So all this data is stored locally and converted into the internal ReMAP data model. And once this is done, this is done in a frequent basis. So when you have new data coming from the airplanes, this data is ingested automatically into the system. And the airline can select from the large variety that in the future there will be in the system of the machine learning algorithms. The operator can decide, okay, I want to run I don't know, a health check for the brakes. So he just needs to download this algorithm from the catalog and run it, and then some results will be shown. I will not enter into much details on the different algorithms because this will be explained later on by my colleagues in the next presentations. Okay, but how, as I was trying to explain, how ReMAP manages the data? As I said, we have several kinds of data. And we made, in this prototype, a very simple interface using a typical SFTP. So you just put a bunch of CSV files with all the data that is required. This data, of course, the parameters depend on the airline. So they have different names for the different variables they are using. But the good thing is that we are mapping, as I said, this into our internal ReMAP model, which later on is stored in the database and allows to run in a generic manner the different algorithms. This is a very good approach, we think, because the alternative would be that the developers of those machine learning would have to implement a specific machine learning algorithm for each specific component and also for each specific airline if they are using different naming for the parameters. So this allows to just implement one algorithm per one component and independently of the airline. So some benefits for the different stakeholders that are participating in the project. Concerning the airlines, okay, if we compare with what they are doing nowadays with this schedule maintenance for the airplanes, we have, on the other hand, that they are collecting gigabytes and tons of data daily, and they need to carry out this maintenance and analytics in an efficient manner. So we think ReMAP can support and help them in doing this very efficiently because we are providing some open APIs and SDK which allow us or will allow them to integrate easily their already existing data from their legacy systems into the platform, so they don't have to develop a new system to carry out this. Also, their data is maintained and stored in their own facilities, so it's in a secure environment. No other one can access to it. And also, they have, in the future, potentially, access to many machine learning algorithms for any kind of components they have in the airplane. And the advantage is that since this will be an open ecosystem where the different developers can provide their own algorithm, this allows the airlines to select which is the best fitting algorithm for them, based maybe on the cost or the price of this algorithm, the accuracy that provides this algorithm, or the resources that are required to run this algorithm. Maybe they don't have enough computational resources and they prefer to have less accuracy, but this is something that can be run in their infrastructure. Also for the developers, this opens the opportunity to them to claim that their algorithm has been really tested with the components, with the data coming from the airlines. So it's a proved and validated algorithm against the data. Also, the ReMAP model allows them, as I mentioned, to develop generic algorithms that can be run for any airline, since they will be complying with this common data model. And in the future, we think also that the ReMAP core can act as a digital marketplace where they can upload their algorithms and monetize them in order to get paid for their work. Okay, but let's not stop here, because in the future, why not to extend this to other parts of the sector? So we have done it for airlines, but why not to apply this to airports or MRO stakeholders? At the end, for instance, the airport has thousands of sensors and different subsections that probably need some condition-based maintenance. And well, this approach could be easily applied and adapted for them. And even better, if we think in the daily operations of an airport where everything is combined, well, we could combine all this data and try to make life easier for running the airports, take into account all these things that can have some maintenance that has to be done regularly. But not only this, in the future we also plan to go a step further and implement the federated learning, and allow to combine the data from different airlines in order for the machine learning developers to improve their algorithms so they can run separately their algorithms in each of the nodes and improve in each iteration the accuracy of the algorithm with new data from a different airline. Okay, not mentioned here, but of course we have an interest in this project as Atos, but us being a global company, we are touching many other different sectors like automation, manufacturing, energy, and so on. So why stop only in the airlines or airports? And this could be much broader and applied to many other sectors where condition-based maintenance is also a key factor in order to maintain the different assets of the companies. Well, that's something that a company like Atos definitely is interested in the future to continue the work on this. Just to briefly mention and just to finish my presentation, the system is currently being tested and demonstrated in an operational environment at KLM facilities. So the core of the system is maintained by Atos in our IT infrastructure, but the airline node is maintained, as I said, in the KLM IT systems. And just some statistics, but this my colleague Floris will explain better in his demonstration later on. This is being just run with 50 aircraft for the moment, with data collected from 100 flights per day, and we have stored during these months a total of 300 gigabytes so far. But you will see more details on this on the presentation made by him at the end. And as Bruno said, this has been a joint effort by all the consortium, and we have been very happy to participate in the project. So, any question?
I don't know if there is one or two clarification questions, something that you didn't get from the presentation you'd like to ask. Just check here, sorry. The chat. No. Okay, so if there are no questions, thank you, Michael. Okay. I'm going to ask my colleague Theo to give the next presentation. Theo.
Theo and my buddy here.
Your body, yeah. You have something to see, to let
Okay. So, well, good morning, everyone. I'm Theo Lutas. I'm associate professor in the University of Patras. And I will try to start the storytelling regarding where did we start on ReMAP more than 5 years ago. And back to these days, we started discussing about maintenance of aircrafts and the way towards CBM, which is a dream, but how we're going to reach this dream. And pretty quickly we realized that there are three main pillars: structures, systems, and planning. With a couple more, but we started thinking that these were the major pillars. And today I'm going to present you, I'm going to start this presentation and my colleagues will follow regarding structures. And how did we work, how did we approach the structural health management? Needless to say that this presentation, my presentation is a joint effort. I'm only the frontman here. All these colleagues contributed very crucially and very critically, all these partners very critically to the rest that you are going to see today. So our goal is to develop and explore the potential of data-driven approaches for the two sub-pillars under the structures pillar, diagnostics and prognostics. Prognostics still at its infancy, but an essential tool towards CBM. And I'm going to show you, I could talk for hours probably, trying to summarize the results of this joint effort on structures, but let me tour you on the main achievements. So regarding diagnostics, the consortium developed several diagnostic methodologies, relying on on different sensing technologies and we can now say that we have methodologies that detected anomalies with percentages higher than 95% regarding the L1 panels. The L1 panels, the L1 coupons are these guys here. I'm going to show you in more detail in a while. It's actually, we went beyond simple coupon level testing. We made more complex coupons, like I would say generic elements of structures, like this single-stringered CFRP coupon, and also multi-stringered larger panels in a hierarchical, let's say, approach. So in diagnostics, we get really good results regarding the diagnosis of anomalies of damage, as well as the localization of damage, and its severity, the severity assessment. We also developed several, again, prognostic methodologies based on SHM data, methodologies that can estimate, can prognose the remaining useful life of a structure. We are in the process of quantifying the metrics in the prognostics because it's still an ongoing activity. So the first achievement was to manufacture and test several elements, starting from level 1 generic elements, manufacturing, and sensorization. More than 40 single-stringered panels have been produced and sensorized, as you may see with PZT sensors. It's these white discs over here, testing for lamp wave testing, as well as optical fibers along the stringers, along the stringer feet, to try to diagnose disbones. Okay, or delaminations, let's say, because it's co-cured. It's a co-cured structure. So we tested in fatigue, and we tested elements, structural elements that have either artificial disbones or impact damage. So they did not start from the pristine condition. So a lot of these guys have been testing, and fewer larger multi-stringered panels, around 8, that have been tested. More than 30 million fatigue cycles have been achieved till today. And you can see a short video of level 1 coupon being tested in fatigue in the post-buckling regime, with all the equipment, all the sensors, all the sensing technologies, various sensing technologies, acoustic emission as well, it's not shown here, DIC as well, and so on and so forth. And these are the level 2 panels that have been tested in this university, in TU Delft, by Dimitrios' team. Do we have the videos here? Nope. It's not playing. It was supposed to play, but okay. You understand it's the same concept: compression, fatigue tests, still failure. And after testing, so we had to test, because I forgot to mention, we had to develop our own data. There are no available structural health monitoring data from real aircraft structures, not available to us. Maybe there are to the airliners, but not to ourselves. So we had to make scenarios of damage propagating in composite structures and try to develop the whole techniques that we talk about. And after testing and gathering tons of data, we started building the various methodologies. One methodology developed by our team in the University of Patras is what we call a digital twin-based SHM. This concerns the development and validation of a digital twin. This is actually a validated finite element model of the physical, let's say, structure. And with the aid of surrogate modeling and with real data coming from the physical twin, from the actual structure, development and methodology that consists of various levels, such as load identification, damage detection, and localization, as well as understanding if damage occurs due to damage propagation or stiffness degradation of the composite as it is fatigued. Another achievement concerns health indicators development out of complex SHM data. The raw data, as it's not working, as one might see here, raw strain data in a fatigue test or raw acoustic emission data in a multi-hour fatigue test are extremely complex. And on their own, they have no information, so have to dig into them to extract what we say diagnostic information, and as well as prognostic potentially information. So to go from there, from uninformative raw data to here, to health indicators with several attributes that we want to, like monotonicity or prognosability, there was some way to be taken that involved a lot of data processing, artificial intelligence algorithms, and so on and so forth. In another achievement, we developed another diagnostic approach based on the data fusion of acoustic emission data and strain data from the optical fibers. So the team in TU Delft managed to combine information from different sensing techniques to answer again all the levels of SHM. Damage detection in level 1, damage localization and damage type identification in the second level, as well as damage severity assessment. The next achievement concerns lamp wave-based SHM and what we could achieve in terms of diagnosis utilizing lamp wave measurements. We have here a lot of work being put by our colleagues in ENSAM in Paris, where they utilized the raw signals, the raw waves, and under certain pre-processing, they also managed to produce damage indices or health indicators, as we call them, and develop a couple of methodologies for damage localization with very good results, as you can see over there, as well as a very accurate damage size quantification, which is also very important. The next achievement concerns a joint effort from the 3 universities of the program, where again we utilized lamp wave measurements to try to assess through the lamp wave measurements, try to assess in real time the stiffness degradation, try to correlate actually information contained in the lamp waves to associate it with the stiffness degradation due to damage propagation or due to the fatigue. The next achievement concerns the build-up of prognostic methodologies. And this is, in this figure, there is the framework. There is the basic framework that describes the whole work over here. The idea is, again, in a data-driven approach, to utilize SHM data from several tests or from several structures, let's say, what we call several K-number degradation histories, and utilize statistical approaches or artificial intelligence tools, neural nets, Gaussian processes, hidden Markov models. We have used quite a few to identify a model that can, in the end, estimate out of SHM data, can, in the end, estimate the remaining useful life. And until a point that we can all agree that defines the end of life threshold of a structure. We managed several pillars are critical here, mainly the health indicator development that I talked about also before. Data fusion can be interesting and important. We have successfully built methodologies like this. We are in the point of assessing how in level 1, and we are in the point of assessing how these methodologies developed in level 1 can be upscaled to larger and more complex structures. And these are some results obtained regarding prognostics, utilizing strain data or lamp wave data or acoustic emission data. In a nutshell, with the bold black line, you can see the actual, you can see the ground truth. In the X and Y axis, it's remaining life. In the Y axis is remaining life being estimated. In the X axis is the actual life of the component. And the closer you are, the closer your estimates are in the black line, the more successfully, the more closer you are to the real remaining useful life. So there are cases that these estimations are very close. There are cases that they are not really very close. But these are some highlights of what we achieved. And when we started this journey, we were not even sure if we could produce good estimates, at least close to the ground truth. And it's a very important for us achievement that we managed to obtain these results. The last achievement out of this whole effort concerns what Bruno said before, an open repository of all this data. All the raw data collected in these multi-hour fatigue tests are, or at least most of them, the majority of those data, the most representative, are in this open repository. available for the community to work, try, experiment, test, and so on and so forth. And I think that this is the last my last slide. I think regarding the impact that we estimate behind this work. So scientifically, from a scientific perspective, we were engaged in some tests that we considered unprecedented with the sense that these are very tough tests and very expensive tests. Without the good funding from EU, we could not produce so many panels with so many sensing technologies on it. We obtained a better understanding of the degradation progression in composites, and also we have the chance to see new phenomena that we previously have no idea that they happen. Several diagnostic and prognostic methodologies were developed and have to be definitely further assessed in real conditions. Regarding industrial impact, I would say that at this point it's hard to quantify and generalize, and especially without the strong engagement of OEMs and MROs, because in the end, we were academics advised by an OEM like Embraer, and we got good advice out of them. But in the end, the engagement of bigger players is needed if we want to go to the direction of CBM of structures, if we want to maintain our structures this way. So I think this was my last slide. Thank you.
Thank you very much, Theo. Any burning question regarding the presentation from Theo? Yes, Marco Olivier. Wait, we have a microphone for you. Is it on? Yes. Yep. It's a dynamic process.
Okay. Oh, wonderful. Yes, Theo, at the end you mentioned OEM and MRO engagement, which is needed. But in your method, is the outputs of what you develop is more oriented to embedded system? In this case, you address your question more to the OEM. And if it's repair or way to improve the repair, in this case, it would be in the camp of the MRO repair station, which is completely different.
Absolutely.
So, so your methods address more embedded system or repair? Or both?
The methods, exactly. The methods are generic. They could be used either way. It depends on what the approach would be, either from the OEM who builds the aircraft, builds the structures, or from the MRO. You are absolutely right that it's a different perspective, but indeed the methodologies, the concept can be applied both ways.
Thank you.
Thanks, Theo. Thanks. Let's move on. Thank you very much, Anarta. If you have to click for some time to show up. Yeah. I don't know. Now it's a presentation.
Hello, my name is Anarta Ghosh. I'm a research scientist at Collins Aerospace Ireland Limited, and I'm going to present the Work Package 5 system-level diagnostics, prognostics, and health management. So before we start, I'd like to emphasize I'm just the front person. This work is a result of hard work of many partners, University of Coimbra, TU Delft, Onera, Artus, our main IT partner, KLM, the data source, and a lot of inputs regarding how aircrafts are maintained at their end. So let's start why we are doing system-level diagnostics and PHM. I mean, what value you'd like to add. So presently, most of the aircraft maintenance follows either preventive or reactive. So preventive is that when you get an equipment, you schedule an interval of inspection-based maintenance, whether the system is okay, healthy, working perfectly or not. You have to spend time and money to do maintenance inspections, and if any requirement is there, if it is degraded, you take some maintenance action. So this leads to over maintenance, like even if everything is fine, you have to spend resource and time to look into the system and component. The other paradigm is reactive. Reactive is when something fails, you react to it, like you have to take an action to repair it, and until it is repaired, a lot of the times the aircraft is grounded. So the airlines lose a lot of flight hours due to such a reactive paradigm. So in the ReMAP, we would like to shift from this very commonly used two paradigms, reactive and preventive maintenance paradigms. We aim to develop something called condition-based maintenance, which Bruno earlier introduced. This is the whole tool chain, kind of whole workflow of a typical CBM. You have the data, you analyze the data, visualize the results, do maintenance. And here you see in the ellipse the main WP5 PHM, where we develop the analytics to kind of monitor the health of the aircraft systems and components. We'd like to see whether everything is fine or not on real time. Every time the aircraft lands, we take the data, analyze the data, run our PHM algorithms, and see how is the health. And based on that analysis, some maintenance action is taken. So it is condition-based. What is the condition of the system and component? Based on that, we take maintenance actions. Now, who gets benefited from it? There are mainly two stakeholders we thought are important here. One is, of course, the end user, the airlines. So they would like to reduce the maintenance cost. Now, as we are not doing preventive, we are not losing this extra over-maintenance overhead. And as we are not doing reactive, we aim to reduce the ground time, like AOG, aircraft on ground scenarios. And also improve aircraft availability. So as reactive maintenance is decreased, we expect to fix something before something fails. So aircrafts are expected to fly more and not grounded due to some health issues. And the next stakeholder is somebody like us, who manufacture aircraft systems and components. We would like to continuously monitor the health, predict likely part failure, component failure before it happens, identify root cause of failures. We would like to have a fleet level maintenance. So we would like to compare the health kind of trajectory of different aircrafts in a fleet, and to see the impact of routes and weathers and other things. Improved warranty strategy and services, the environmental impact, what I said on the health of the components, increased reliability, and one last crucial thing, reduction in the no fault found scenario. So when we get some components, sometimes we see that nothing is wrong, but it had to be removed because there were some issues found in the field. So given this rationale, we aim to develop aircraft systems PHM algorithms. But why yet another effort to develop PHM algorithms? So let's see what is special about ReMAP PHM effort, because PHM is a very hot topic now, so to say. It is a lot of research going on in academia, in other institutions. So how we'd like to add value through ReMAP efforts. So most of the state-of-the-art PHM is still a lot of subject matter expert and domain knowledge based. So you get the data from the aircrafts. We analyze the data with the subject matter experts. We get insight into which data to look into. And based on that insight, the analytics is developed, and then the analytics kind of do all the PHM. What we would like to do is that we would like to see whether we can automate the process, because this is time consuming and it requires maybe decades of experience and domain knowledge, which goes into this SME part, subject matter expert part. So we would like to see that whether we can automate. We get the data, now we would like to develop machine learning algorithm with explainability and kind of do a failure prediction, continuous health monitoring, and remaining useful life estimation based on fully database automated methodology. Now, in addition to this automation, we also would like to see how the results of this automation is useful at the end. Because for the end users, the graphs and plots and the numbers don't matter much. They want to see visually or want to see something actionable. what they need to take. I mean, a plot might not mean much unless they kind of deduct or kind of which leads to some kind of maintenance action. So we've put a lot of emphasis on visualization, how we can visualize the component health degradation from healthy to the failure state, where we are in that trajectory. So here I show you an example of how we develop cutting-edge visualization. Another one, remaining useful life. So remaining useful life is a very kind of, we are trying to predict the future, how long the component will last. It's a tricky concept, so good visualization gives better understanding, facilitates the end user to understand what is going on and how long they have in a much structured way, and that structured way of understanding leads to better maintenance action. In addition to that, here you see everything is around the data we get from the aircrafts. And aircrafts are run by airlines all over the world. So the data is also distributed all over the world. And sometimes due to some administrative issue, legal issue, we cannot get all the data in a centralized location. So we cannot train our PHM model with the centralized collection of the data. In those cases, we need to send the model to the data, to different locations all over the world, and then train those models distributedly and bring back the models and have a centralized model based on the information content which is distributed all over the world. And that is what we called in the research federated learning. University of Coimbra or Colib explored federated learning strategies for aircraft PHM. And this is actually very important due to this legal issue of getting data from different jurisdiction to a centralized location. So we need to develop methodology where we can use information distributed all over the world. So this is how, in the ReMAP, we would like to add value to the present PHM research and kind of extend the frontier. Now, as you see, everything is around the data we get from the aircraft. So we consider two scenarios as per the availability of the data. So first is the PHM scenario 1. We started with this scenario where enough confirmed run to failure data is available. What is run to failure data? An component fails, and you have the data prior to the failure for, say, 100 flights up to the failure. So when we have enough such data, say, many 100, 200 run to failure data for a system or component, then we use such run to failure labeled run to failure data to train our machine learning based system. We started with this also due to a bit of delay of getting real data, and we are getting run to failure data from publicly used databases like NASA PHM database. They have many data sets of run to failure data. We chose the gear turbofan engine data. And here a typical run to failure data is shown here. So this is the system. The data is coming and it fails here. You see the degradation starts from here and it fails. And a bunch of such data, say 50 such run to failure data, is fed into our ReMAP PHM algorithm, which is called TrajectNets. It is a deep learning based methodology. Basically, we use deep learning because we don't want to do any feature engineering or anything like that. We would like to just train the system with raw data and get the results. This is a recurrent neural network-based autoencoder. And what this gives is a kind of, after training, a kind of failure space. And using the embedding of this data into this failure space, two-dimensional failure space, we do the failure prediction, identification of failure type, continuous health monitoring, RUL estimation, and explanation of the prediction. Now, with this figure, it might not be clear how it looks. So let's see when we deploy such system, how it will behave. So here you see the data is coming from the aircraft, and after training, we have created this failure space where this yellow dots region around the yellow dots represent the healthy region, and these red dots represent two different failure modes. So when the data starts coming from the system, so this is each timestamp, we are getting the data. Each color is a given variable. We have, say, 20, 30 different variables. Those are embedded into the failure space. Here, the yellow dots are embedding, and you will soon see that when the degradation starts showing up in the raw data, these yellow dots, which are embedding of these variables at each timestamps in this failure space, we start moving to one of the failure modes. So here you see it is not only analytics, it's also a very cutting-edge, nice visualization we see. And in the field, the end user then can see, okay, I am moving away from the healthy region and moving towards this failure mode. So I need to prepare for the maintenance action. So I need to see where my spare parts are. I can route the aircraft according to the availability of spare parts and take maintenance action. Now, this is, in terms of results, we got very good results, and it's a published work in International Journal of PHM. So you can refer more details about this work. So this is PHM scenario 1 when we have a lot of labeled run-to-failure data. Now, when we start getting the real data from the aircrafts, we saw that it's very difficult to get a lot of labeled run-to-failure data. Aircraft systems don't fail very often, especially safety-critical systems and other very essential systems. They are made such a way that they are supposed to last long. So we had to consider a different scenario called PHM scenario 2, where what we do is that we get healthy data, operational data, because we don't have the run-to-failure data, and train a different machine learning-based methodology called PHMNet. I'm not going into detail about that, and create a different subspace representation of this data. And using that subspace representation, we predict failure. Now, how this will look when we deploy. So earlier we saw that we created this failure space, but here we create the healthy space. And this is data coming from the aircraft, and this is embedding of the data in 2D space. And when something happens, you see that the embedding goes away from the healthy space. And here I show you the health and the distance from the healthy region. And we predict failure based on this deviation from the nominal operation. Now, this is good. We predict failure. We ask the maintenance MRO group to take action, but they will ask us why. I mean, this looks good, but this is all like a voodoo to them. So we have to give some more real explanation why we are saying that the system health is degrading. So here I show you some results of explainability. I'm not going to detail into that. So here basically it shows which part of the system is degrading, and based on those information, a more targeted maintenance action can be taken. So what are the advantages over the state of the art? We don't need to monitor each signal. We can have a global analysis and get the health of the system at every timestamp. As you saw, it's a cutting-edge visualization we have, highly reusable. We can move from one system to another system within 1 hour, 2 hours. You don't have to spend weeks or months discussing with subject matter experts to develop the next PHM for the next system. Requirement, we need historical data from healthy operations. And most importantly, to predict failure, something must change in the data what you're measuring from compared to the healthy operating conditions. So then only we can predict failure. So this kind of ends most of the core PHM work we have done, but how it fits into the maintenance, because that is the ultimate end use of it. It has to lead to some maintenance action. So here I show you schematically how the PHM results are fed into the maintenance. We have failure prediction, we have explainability, root cause analysis, and then maintenance action can be taken based on these two information, and optimized maintenance will be carried out. And then in the PHM scenario 1, we have more detailed information because the data is richer here. Here we give the remaining useful life, health index, failure probability, and based on that, optimal maintenance can be taken. And I think this is my last slide. Yeah, so that ends our work, a kind of presentation of our work on the PHM.
Thank you very much, Narta. Any question regarding this presentation that you'd like to ask before we move to the next one? So questions will be at the end. Thanks, Narta.
Yeah.
So let's move on, Paul. Yes.
Both from the TDAP side as well as the KLM side. And what WorkPackage 6 is all about is developing a maintenance decision support. Because as we have seen in the previous presentations, we came up for solutions for structural health monitoring.
Yeah? This is perfect. All right. So, just a very quick recap. So, as we have seen in the previous two presentations, we've came up with solutions for structural health monitoring as well as prognostic health monitoring. But then the question is how to apply this within a working airline. And that's what we investigated in this work package. Because what we see here on the picture is what's called the OCC of KLM, and it stands for Operational Control Center. And this is the room where all divisions of the airline come together. And we try to keep our operations running as smooth as possible without delaying flights, without canceling flights, etc. And one of these aspects that's taken into account here within the OCC is execution of maintenance, or keeping the aircraft airworthy. Because as long as we do our maintenance on time and the aircraft don't break down unexpectedly, then we hope that we can at least provide the aircraft for operations, and then of course other aspects come there together as well, such as crew, such as baggage loaders, all the things, all the pieces of the puzzle should come together. So if we take a look on how we plan maintenance, then there are basically three elements which have to come together. If we start here in the top left, the slot schedule, that's the time that's been put available to execute maintenance. So the aircraft doesn't need to execute a flight, and it's standing on the platform or standing in the hangar and available for our people to maintain it. Then, of course, you need to decide what to do, and that comes from the maintenance tasks that need to be executed. And then at last, the resources need to be available for execution of maintenance. So you need to have the people available, you need to have the tools available, as well as the material. But if we zoom it or if we're going to zoom in a bit on what kind of maintenance do we have to execute, what are the tasks that we need to execute. Currently, if we look mainly in our current operations, there are two categories. So we have our routine maintenance. These are prescribed by the OEM of the aircraft, and it says that it's a big list of tasks, and each task has a specific interval that you need to do. Some tasks you need to do every day, some you need to do every month, some you need to do maybe once in the 3 years. Then secondly is corrective maintenance. So this is when the aircraft breaks down and you have to fix it. And of course, we would like to prevent this as much as possible. That's why there is routine maintenance. But that's also really what we have been investigating within ReMAP. We would like to predict if an aircraft is going to break down. And that comes now from two sources. So we have, we researched two aspects, which are the SHM alerts and PHM alerts. So because what, of course, the ultimate scenario is that we get an alert upfront and we see that some component or some part of the aircraft is breaking down. And without it actually failing, before it fails, we can already take it into the hangar, replace it, and and then the operations are not disrupted. So what we try to do is to prevent that the alerts that are coming from SHM and PHM become actually corrective maintenance, because that can cause big disruptions. Some of these failures cause that the aircraft is grounded immediately, and that means that sometimes also you have to cancel flights for passengers, and it's of course something that you would always like to prevent. But to come up with a way of scheduling and adapting the schedule for these SHM and PHM alerts, we have to come up with something in between. And that's where the first model comes into play that we developed within WorkPackage 6, which is the POMCP model. And POMCP stands for Partially Observable Monte Carlo Planning Model. And what it does is that we receive inputs from prognostic models. They give a remaining useful life. And that basically means, so every day after an aircraft touches down, the data is shared to the cloud, the prognostic model is being run, and then as an output of that model, it says, okay, we expect that this model can survive for, let's say, another 120 flight hours. If we know that it survives for only 120 more flight hours, we would like to schedule it before it reaches that threshold, such that it doesn't fail unexpectedly. And what the POMCP model does is taking this uncertainty into account, because maybe one day the aircraft touches down, it says 120 days, and maybe the next day it says, oh, no, it performs slightly better than expected, so maybe it's 130 days that it can still survive. So what the POMCP model does is to try to find the optimal point in the maintenance schedule that we can execute it. So we try to find the day with the lowest cost for execution. And this is actually also running on the ReMAP platform daily with the new PHM data that comes in as well when the aircraft touches down. So by having this solution developed, we have now also the PHM and potentially SHM tasks which are in our list of tasks that we need to execute. For SHM, of course, yeah, the sensors are unfortunately not yet installed on the aircraft, but the method of working would be identical to PHM tasks. And then if we receive an update every day, that may also cause that we need to change the schedule. Because within the airline, disruptions are taking place daily, and that can come in the form of a new update on PHM information. But it could also be because of a whole other range of factors, such that maybe an aircraft broke down and a component needs to be replaced earlier than expected. But it could also be, for example, a flight which arrives delayed at the airport and was scheduled for maintenance, but then the maintenance can only schedule later than planned. So then the question is how to revise such a schedule, because with dealing with such a tremendous amount of data, you need to be adaptive to new information and making sure that you keep your fleet operational, such that always we have enough aircraft available to perform the scheduled flights. That's where the second part, or the second model that comes into play that we developed within WorkPackage 6, is this disruptive process. So we have a currently existing maintenance schedule, a disruption occurs, which requires a change in schedule. How can we reschedule this most efficiently and that we can have a feasible schedule in the end? So actually we have two solutions for this at the moment. And the one which is currently running on the ReMAP platform is the MRLP model, which stands for Mixed Integer Linear Programming Model. It basically gives an outline in which we can define all sorts of constraints from the KLM operations, as well as the objective, which we try to optimize. And there are actually quite a lot of objectives that come into play when trying to create an optimal maintenance schedule. The first one of that is task execution. So we have our list of tasks, especially the routine and corrective maintenance. It's by law or by regulations required that we execute those before the deadline of that task. Because if we don't do it before that deadline, then the aircraft is stuck on the ground. So that should always be the main objective. Try to schedule a task before it reaches the deadline. But let's say if we schedule each task at the deadline, then it could be that the aircraft will be grounded every day. Because maybe every day there goes a task goes due. So that's why also the second objective is ground time management. So you would like to do it as efficiently as possible, such that the first objective is keeping the fleet airworthy. Second objective is to do that in the least amount of time possible. And then afterwards, it comes down to the third objective, which really relates to the disruptional aspect, is that once we receive new information, so once there's a data update, you don't want to make a complete new schedule again, because that's the people in the hangar and or engineers, etc., are not able to work with a schedule that changes every 5 minutes. So what the third objective is to prevent the amount of schedule changes, to make it as constant as possible, and that only the required adaptations are made if it really impacts the airworthiness of the aircraft. But actually, when we are taking PHM and SHM tasks into account, there is an additional challenge, and that is how to schedule these prognostic alerts. Because they do not really fall in this first category of task execution, because if we exceed the deadline of a SHM or PHM task, then it doesn't necessarily mean that the aircraft is not airworthy anymore. There's just a high risk that it will fail very soon. So that's why there's a trade-off to be made. How much ground time are we going to use, and when are we going to schedule our prognostic task? So it might be worth to use a bit more ground time, but that we can make use of all our prognostic alerts. And that's a bit of a trade-off, and we performed that trade-off offline with varying the relational factor in between, such that we could come to an optimal ratio. And that ratio is really depending on the airline preferences. So we within KLM came up with some ratio, but also another airline might value more to give higher priority to prognostic tasks, for example. And what's really important is that this is also updated with live data on the ReMAP platform. And that's quite a big achievement, because we never used to have this data available to us live, that we get the updates like almost instantly, like there's a 30-minute delay in there. So once something is changed in the inputs, then 30 minutes later we have an alternative solution, because currently this is a process by hand. So now we can take both the SHM and PHM alerts into account, and we can revise the schedule. But not always, you cannot always get all the information out of the data. And that's why also there always needs to be a human in the loop, somebody who supervises the schedule and adjusts it or gives additional constraints when needed. And that's why, as the last part of Work Package 6, we've also developed a user interface in which the schedule can be observed. And to give you a brief look of how that looks, it's displayed here on the slide. So blue parts are flights, orange parts are maintenance blocks, and then also once you collapse this block, then you can see the tasks that need to be executed. Actually, in the break after this, for the people here attending here on location, George will be displaying it on the TV screen, and I highly recommend to take a look at it, because it's really intuitive and gives new insights of how maintenance is being scheduled. And actually, that brings me to the end, because then the loop is completely closed, such that there's feedback from the specialists, and then we have the models supporting it. And of course, my presentation only gave a brief conceptual outline of how it works, but if you're interested, then feel free to contact any of us to give a more elaborate explanation on how the models itself worked. That's it.
Thank you very much. There is a question from colleagues online, how the data is inserted in our platform, so how the live data is collected and used in our platform.
Okay, yeah, that's actually a very good question. So from KLM side, we built a data pipeline. So we have our online administrative systems, which we have our maintenance records and also the future maintenance requirements. And what we've done is we have created a pipeline which automatically extracts this data from the IT systems from KLM and sends it to the Atos platform. And that's done every 30 minutes. So every 30 minutes, Atos or the node receives an update in the form of CSV files. And then once these data is loaded into the platform, it's also available to our planning models.
Yeah. It's important to say it's Atos platform, but the node, so the airline side, so it stays at the airline.
Exactly, yeah.
Any other question? No? Okay, so I propose we have now the coffee break. We are already running late, but no problem with that. I still propose that we take our time to refresh and come back. So we'll be back at 11:40 here. And then we'll have two other presentations. One from my colleague Michele Mitici that will talk about risk and performance assessment. And then Floris Freeman will talk us about the demonstration itself. So we'll see each other here at 11:40. In the meantime, could go downstairs. We'll have coffee and snacks for you to enjoy. Thank you very much.
tell me that you love me. I dream of you whenever I'm not with you. My love, my love, my love for you. I believe it. My love for you, my love for you. You tell me that you love me. You tell me that you love me. I dream of you whenever I'm not with you. My love, my love, my love for you. I believe it. I believe it.
Okay, so welcome back, everyone. I'm Mihaela Mitici, assistant professor at TU Delft, Aerospace Engineering Faculty, and I will present to you our results obtained for Work Package 7 within ReMAP. And this regards a multi-objective perspective and a dynamic assessment from a multi-objective perspective of aircraft maintenance. This is a joint work with my PhD student Jusong Lee, as well as with several collaborators from ONERA and KLM. So let's get started. Why a multi-objective perspective for aircraft maintenance? We are looking at several aspects. From a cost perspective, we want to minimize the number of inspections, the number of replacements, and especially unscheduled maintenance. All this costs money. We want to be as efficient as possible. But we don't want to be to create cost savings at the cost of, for instance, having more degradation incidents. And that's where the reliability and safety part of the maintenance process lies. We are also interested in increasing the availability of the aircraft. We want to minimize the delays related to maintenance and many more. Therefore, we have a multi-objective perspective of the process. And we want to see if we can achieve a balance between such multiple key performance indicators. How do we do that? How do we assess that? We propose to first understand well the maintenance process, to identify the system and the agents involved in the system using an agent-based model, and then to formalize the agent-based model using stochastically and dynamically colored Petri nets, which are formal representations that take into account the uncertainty, the degradation of components is a stochastic process. The amount of time needed to do maintenance is also stochastic, and so on. And here you see just an example of a Petri net, stochastic Petri net. There are two agents, the mechanic and the aircraft, that needs maintenance. And from places, the circles, using tokens, in time we can generate the interaction between agents, taking into account, again, the dynamic process of aircraft maintenance. We integrate in such Petri nets new technologies, such as data-driven remaining useful life prognostics, and we use Monte Carlo simulations to evaluate multiple key performance indicators. I mentioned the system identification of the maintenance process. We discussed in collaboration with the KLM partners and understood the general process from task-generating teams who prescribe what type of tasks need to be executed by a specific deadline. Then the task planning team, which actually makes a schedule of those tasks to make sure that they are executed before the deadline. The mechanics who execute the tasks. Flight crews who provide also feedback about the condition of the systems. And we have a new agent, as more data becomes available, the data management team, we call it, who is actually making use of sensor measurements and informs the task-generating teams and the task planning team to make the best use out of this additional information. We applied our framework for the aircraft landing gear brakes. We generated, based on data that monitors the degradation of the components, we generated remaining useful life prognostics. We also, here you can see some measurements after proper normalization of the degradation of the carbon disc of landing brakes. Here you see also the uncertainty quantification related to this degradation. And as I mentioned, we inserted this type of information in stochastically and dynamically colored Petri nets. So we trigger, based on our prognostics, we trigger alerts that will justify the maintenance tasks for these brakes. So just to see how it looks like, the tokens over time change places based on the stochastic degradation of the brakes. Using Monte Carlo simulation, we were able to analyze different key performance indicators. Here you see two conflicting key performance indicators, the mean cycle to replacement, which is an indicator of the cost. So the shorter the mean cycle to replacement, the more frequently you replace your brakes, let's say. But the more frequently you replace your brakes, the more costs you have. But the more frequently you replace your brakes, you have the lower chance to have a degradation incident. The other way around, the larger the intervals, you have less costs, but then you may risk to have an incident. So how to trade between that? And we looked primarily at strategies where we actually use remaining useful life prognostics for replacement of the brakes relative to fixed interval maintenance. So what was happening in the past, where let's say every month or so we have an inspection or a replacement. And we saw, our results showed that actually by using remaining useful life prognostics, we are in the near region of a Pareto front that trades off between the number of incidents and the number of mean cycle to replacement. What does that mean? It means that using rule prognostics, we are able to find the best trade-off between degradation incidents, the number of degradation incidents, without sacrificing the cost savings. A similar result was found also for the mean cycle to replacement and delays due to maintenance. Again, we see that if we actually use prognostics, we are again in the near region of the Pareto front of these conflicting key performance indicators, which means that rule-based prognostics is again beneficial in achieving the best trade-off between both delays and mean cycle to replacement. If we were to summarize the impact of our work, I think it's important to stress the fact that we proposed an innovative framework to assess CBM technologies, and in particular new CBM technologies, so in advance of their implementation in real life. We had a system perspective with the support of our KLM partners, so we understood the process from the industry point of view. We had expert validations. We discussed with them what the hazards related to CBM technologies, new CBM technologies may be. And we also derived some data-driven rule prognostics to be able to implement them in our framework. And I think we are also very happy to see that together with KLM, we were able to apply our methodologies in realistic case studies, and in particular for the landing gear brake. So with this, I would like to thank very much our partners, Onera, for the nice discussions and support, as well as KLM partners. Without them, this wouldn't have been possible. So thank you.
Thank you, Michael. So questions about this presentation? Yes? No, but then in the live, people cannot hear. Yeah. People online are missing this fun part.
Do I have to put it on? It's on. I was wondering, because you're talking about this case study, landing gear brake, what are the other case studies that have been looked at or should be looked at?
For assessment, we didn't manage to extend our analysis for other systems or structures, so it was not possible. It also, due to time, partners had the need to explore more such case studies, so we just managed to illustrate our framework for the landing gear brakes. Yeah.
And what would be then, in your opinion, for the next project to be really looking at?
I think we can
Other
definitely
components.
extend very easily this type of assessment for other systems. Maybe a system of systems in the sense that some systems have redundant components, so it would be interesting to look into the redundancy of such systems. Yeah.
Okay, thank you.
Thank you very much. So, move to the next presenter. Floris, please. The pointer is somewhere here. Yeah.
Okay. You can hear me, I think. Just waiting for the slides to come up. I think it's 5 minutes before lunch. I know I was before lunch, but I hope I won't be instead of lunch. So I'm going to speed up through the presentation a little bit. Good. So with KLM, we had a very nice opportunity to be able to test all the cool technologies that were just presented. And that's what we did in the 6 months demonstration phase. But that's not all we did. We wanted to know where are we now in terms of condition-based maintenance, where do we expect to be in the future, and what can we do today? And that's how this work packages was also structured. So we started with an analysis of the current state. How does maintenance look like? Where can CBM play a role? Where does CBM already play a role, right? We already do maintenance based on the condition of the aircraft, of course. Then see how these technologies that have been developed in Work Package 5 and 6 perform. And finally, what is there to gain? If you scale this up, if you have more projects like these, where are we going to be in 5, 10, 20 years with CBM? How much value is there to gain? I'll address the first 2 items. I think most of you came for the demo, but I think it's interesting to talk a little bit about the current state as well. Because we wanted to know, where does our time go? We buy an aircraft for maybe 10 years, 20 years, maybe even longer than that. Ideally, you want to fly for that many years as well, right? So if you have a week of aircraft at your position, you want that aircraft to be in the sky for a full week, ideally, because that's when you make money. But when you look at where our time goes, so how much do we actually fly in comparison to how much do we have the aircraft on the ground, then you see that well, maybe roughly half of the 50% of the time you're actually flying. So where does that time go? And we could do the same for the dimension of cost here to see where benefits of CBM could lie. But I like to do this in the dimension of availability. So we did an analysis to see what happens with our time. And we could see that already a lot of time had nothing at all to do with maintenance, right? You need to have passengers on board and off board. You need to fuel the aircraft. There's a lot of stuff you need to do. For some airports like ours, you cannot fly during the night. You cannot do landings and takeoffs during the night. So that already consumes a big portion of the time that you have for flying. And what is left is what you see here in orange. So those are the parts that do consume time and are part of, are basically there because we need to do maintenance. So it's 3 components. One is planned maintenance, which are the A checks, the C checks, basically everything that we know is going to happen up front. So planned maintenance. A second is unplanned maintenance. I'll address this in a bit, but there's still, Anarta addressed it as well, by the way. So part of the maintenance philosophy is also reactive maintenance. Some components are not so critical, and it's operationally, economically, and also safe to have them fail and then correct them. But it's still a nuisance because you need to address it, and it might ultimately lead to a delay or a cancellation. So planned maintenance, unplanned maintenance, and then there's buffer. So if you don't like to have a delay or a cancellation, which many airlines don't, and many people, by the way, also don't, then it could be a good idea to have an aircraft on spare, or maybe even 2, so that if there's an unexpected disruption, you still have a spare aircraft that you can use. So these are the components here where CBM could play a role. And I'll address briefly how. First of all, CBM could make these length of these orange blocks shorter. So, for example, if you know your condition of your aircraft up front, you don't need to have it on the ground to inspect that condition. Then that saves a lot of ground time. You can do fewer tasks basically. Also, if your troubleshooting is faster because you have prognostics, then you need less ground time too. So the quantity expressed in number of tasks or total duration of task is one where CBM can help. The second one is efficiency. And so if you look at basically mostly faults, you want to address them as quickly as possible. But let's say that every 2 flights create a fault, then every 2 flights you have to do you have to address these faults. Whereas with prognostics and predictive maintenance, you can anticipate them, and then you can do multiple faults. You can mitigate the impact of multiple faults at the same work package. You can have your work package much more efficiently by means of parallelization of work. And thirdly is timing. So if you can anticipate that something is going to be failing or faulty, then you can address that in a more convenient maintenance opportunity. And this is an example where you could do that, for example, during the night, where the aircraft is not able to fly anyway. I'm going to highlight one more thing. We wrote a nice report on the current state of maintenance. I like to show this as well, because as I said in the beginning, we already do condition-based maintenance. It's not completely new. And as you can see here in this plot, already about 20% of tasks are done on condition. So either the aircraft detects that there is something going on, or the crew detects it. And the remaining 80% is those tasks that are done based on usage parameters like number of landings, number of flight hours, or calendar days. So that's 80%. And if you then check in that 80%, what are you actually doing in that 80%? Then about half of that is just a state assessment where you don't alter the configuration of your aircraft. So you have to see that as follows: the aircraft comes in, you do a check, you see that nothing is wrong, and then the aircraft is back to service. But this is, of course, a system that we really need to make flying safe and to have the fleet in an airworthy state. But intuitively, you could also see that it's not super efficient. If the aircraft comes in, nothing needs to be changed, and then it's back in the air. With CBM, if you would know this condition up front while it's flying, then you don't need this time. All right, let's go to the demonstration. A lot has been said about the IT platform. This is the IT platform that Atos built. We installed it, at least the node, so the part that is installed at the airport. And there's still the core that hosts all the models, which is hosted by Atos. Briefly, the idea behind this architecture is that no airline on itself is facing enough technical problems to be able to train AI. So we need to combine data from multiple airlines. I can probably predict that it's not just KLM that doesn't have many of these problems. We have problems, but not many of these technical problems. It's also our competitors and other airlines. Failures and faults are just very, very rare, fortunately. So we need to combine data from and problems from multiple airlines, so that you just don't have only healthy data, but you also see unhealthy data. But then there's the reluctance of airlines to share data for various reasons. So the architecture here enables that the models can travel from airline to airline and iteratively become a little bit better each time they visit one airline. So unfortunately, we were the only airline here in this project. I think COVID didn't help. I think with the new project, we might be able to test federated analytics in this platform with multiple airlines. But for this demonstration, we were the only one. We connected our data, our sensor data, but also our planning data, our slot data, basically everything that Paul just showed in his graphs. And we also invited all the model developers from the project to upload their models to the core. And then for us, the only thing we needed to do is download those models like it was an application on your phone in the App Store. You just download. You can also do update or delete, and then it runs. It's really as easy as that. I think this has been already covered. So we had 50 aircraft, two types, the 787 and the 737. We also did some work with the Embraer fleet of KLM Cityhopper, but those, it's a different company, different data pipeline, so they're not in the live real-time demo, but we did work on their systems as well. Okay, so these are screenshots. Maybe we have the opportunity later to show this, how this looks. We can play a little bit with it. So on the left upper corner, you see the model catalog. This is the App Store. You can see that we already have quite a bit of models there. I think we have about 10 covering 8 systems, but also planning models. And really, it's a matter of installing it, and there you go. You can run it. On the right bottom corner, you see an example of a health indicator. This is an air cycle machine. We had a couple of examples. We like this model. We had a couple of examples where we did maintenance based on these health indicators that were coming out of the platform. And the other two diagonals, you can see, well, actually, Paul already showed this, but this is the nice visualization that the colleagues of Coimbra made. Okay, so I'm coming to a conclusion. I think we can say that this platform works, and the model, it can host models, we can run it pretty easily. Once you get the details of the SDK, it takes only I don't know, maybe half a day or so to modify your model such that it can be uploaded to the core. And from that moment on, in theory, all airlines could just download your model, which I think is really cool. We have AI running from work package 5, so that's the prognostics, diagnostics, but also from work package 6, which is the planning. And we have 5 maintenance actions triggered. It's difficult to state whether those actions actually avoided a delay or a cancellation, because you never know, when the failure would happen and where in the world the aircraft is. But yeah, I think at least we have some pretty significant benefit from here during this demo. We're still running it for 3 more months. So I don't want to give the impression, though, that we're there and that from tomorrow onwards CBM is solved and we're done and we can focus on something else, because that's really not true. We faced that data, the big volumes of data was a challenge. So I was on the phone with Atos, Ivan, almost every week, I think. I spoke with Atos more than with my own colleagues, because sometimes a container was full, or sometimes a model was loading too much data. So in the design of this platform, you really need to make sure that it can host that much data. And Anarta also mentioned that AI in principle is not necessarily actionable, right? So if you have a health indicator, but you don't know which of the 4 components is faulty, well, then it's just too expensive to go to the aircraft and check those 4 components. It's not the idea of what we try to achieve with condition-based maintenance. Okay, conclusion. So I think we proved that for that 20% of faults that are of maintenance that is already on condition, we provide a very good benefit, because we can anticipate those faults and we detect them before the aircraft detects them, and that really solves a couple of problems. But for the substitution of tasks that are based on intervals, we could not do that much in this demonstration, and that's mainly because it's simply not allowed to deviate from the aircraft maintenance program, so we didn't. And also this is difficult, because there's not a lot of, virtually no failures of the components and the systems and the structures that are maintained preventively. So here really something else is needed, and maybe it's different sensors, or maybe it's a redesign, or we still have some work to do over there. On federated analytics, I really like the platform that's there that is facilitating federated analytics, but we need to test it. So we need to team up with at least one other airline and test it and see how it really performs, how easy it is, and whether it's actually viable for a large-scale implementation. And then secondly, this is not something that followed from the demonstration, but more my personal opinion. I think we sometimes made ourselves pretty difficult by looking really in the small details of very small parts that could fail. And perhaps what we could do as well is zoom out a little bit and manage the condition of our fleet. So manage the number of deferred defects, the number of tasks that are open, the dispatch penalties that these aircraft have. Because all that data is already there. We don't need more sensors for it. And I think that can really help as well, making our maintenance processes more efficient. Thank you.
Floris, there's already one question. We need again the... Yep. Thanks. Go ahead. Marcel?
Thank you, Floris. You mentioned that the volume of data is a problem. Is that moving the data from the aircraft to the ground station, or is it from the ground station to Atos?
So we have, I think, at least 4 or 5 years of experience with downloading the data from the aircraft to our servers. So the problems we encountered were not in that phase. It was really to load them into the platform and making all the models that might have been trained assuming smaller data volumes to make them work. So it was really the last step from our servers to the Atos platform and then feeding them into the AI models. I think that was the main challenge.
Did you consider edge computing, like doing stuff on the aircraft already?
Yeah, we did, but not for the demonstration. So colleagues from the University of Coimbra made basically experiments to prove that concept, but it's not something we did in this demo. Yeah.
Florence.
Hey.
Yeah, my question is the same line. You showed some data that each aircraft has roughly 6 giga information per aircraft. You know this is stable, it's keep growing, the volume of the information?
What we did do in the beginning is we did scope the number of parameters that we were logging. There's thousands, if not tens of thousands of parameters that we could log, but we already knew that we only needed a subset of a couple of hundreds of parameters. So we did do that pre-selection up front. And from that moment on, of course, the number of growth of data is predictable. It grew steadily, basically. But slowly in the demonstration, we ramped up into more aircraft. We wanted to cover our full fleet. We want to cover more systems. And by scaling up in that way, more and more data became available.
For current world standards today, is all this data is not too much. But I know for MROs, depots, we usually don't have nice internet links to upload all this information.
Yeah, indeed. There's technologies to deal with that data, with that volume of data, but I think it's something that you already need to account for in the design of an AI model, right? So we use a lot of pandas and Python, and maybe if at the beginning we put a requirement that you needed to go for like a big data solution there, then it would have been a little bit easier, indeed, yeah. But all the problems we did have, we could solve by just asking for larger disk space and a bigger virtual machine. So it was manageable, but it was just a bit of work. Yeah.
Thank you. Another question here on this side. Yep.
This is not a question, actually. This is a couple of comments in support of what Floris just presented. So on the topic of how far we are, ReMAP was a research and innovation action project, and our starting TRL was TRL 2, and our target TRL was TRL 5. I think through the demonstration and great job, Floris and others we have done, we have reached that, but TRL 5 is not enough to be productized or deploy in the field. So that's also, it's that we are in the kind of realm of requirements, and we reached that. So further research is taken. Another thing is that we talk a lot about volume of data, and we are collecting huge amount of data. So one thing we should note at some point is that all this data is already there and used by other systems or other functionalities like control and other. Very few of these data actually PHM specific. Like those data are not specifically collected to do health monitoring. So further TRL progression, that might be also a critical issue to have the kind of sensors which is specifically installed to monitor the health. So these two are the basic things I thought maybe what Floris presented, just to remind that this is a research and innovation action project. Real target is 5, and also the data needs to be rethought, and sensorization also should be at some point looked into to have CBM fully operational in the field. Yeah. Thank you.
By the way, join us. Because what are we going to do now? Let's leave this here because there may be questions, and then you share it with you through it. Can I have a micro, Jeremiah? Yeah, 2 micros. Thank you very much. So you don't have a mic, so you can keep this one. We're going to have to share it, okay? So what we're going to have now is a discussion of the overall project. So if you have technical questions for any one of us, I don't think that Miguel is here. I don't know if, Ivan, you want to join us if there are questions about the platform. So if you have any question about how the project went, technical aspects, please, now it's time. We'll have about 30 minutes here to discuss. Of course, we can continue downstairs as well. By the way, downstairs, there is a colleague from the University of Coimbra showing the user interface in the big screen. As Floris said, we can also show the IT platform later on. So please also engage with the colleagues downstairs. But for now, I see that Anchieta has already a question, so please start it.
Sorry about in the demonstration. We have this one representative, this guy, this Delta participating here, David. I talked to David about this opportunity for 1 second evaluation about the system, the ReMAP system. And David talked about this is very interesting for try and test in Delta for verify this system. It's for us is very interesting, yeah. Okay, this David.
You already said it.
Okay, David. Your opinion?
Sorry.
Yeah.
Drop the ball.
Give the ball. Give the ball to David.
All right, thanks for being volunteered. And chat, yeah. But yes, he very much makes the point of, I think one of the next steps we need is more in-service evaluation, more in-service data. You mentioned TRL5, where we get the next. So yes, I think you can count on Delta. I think you can count on KLM. There's at least one other airline in the room.
Yeah.
There's a couple of, I would say, early adopters, and I think you can probably lean on us to get some of more of that data.
Any questions? We have there Marc-Olivier.
Maybe related to what David said, so more practice on the new processes. But I was wondering, at the end of the last presentation, it was said that I identified two showstoppers. One was that the AI was not all actionable, and the second one is that the maintenance program is fixed. And so in the two cases, who is owning the maintenance program and who maybe can improve the actionability of the AI? It's probably the equipment manufacturer as well as the airframers, because they are owning also the repair. And so I would have been interested to have the opinion of the KLM representative. Does it mean that in addition to the practice with the ReMAP processes, do you think that teaming with the airframers, more with the airframers and the equipment manufacturer will help to make AI more actionable? Maybe you can improve the models or the data-driven approach and also adapt the maintenance program that would be easier for you to really integrate the PHM approach with the consequence and into the repair scheme and schedule?
Yeah, you're on.
Yeah, so on the models, to make it specific and make sure that the output exactly tells you what to do, I think there's a role for the OEM indeed. They could definitely help and try to make sense of what is the output of the AI, but I think the model developers themselves can also play a role here. So there's been different approaches. For example, colleagues from Onera, they made models for very specific parts, so that if that model gave an alert, you would know exactly already that it's this subpart. Other developers made models for more of a generic or a bigger level system. And there it was a little bit more difficult to know, to pinpoint what was the subpart that needed to be replaced or inspected. I think Anarta also showed an example of where you can just, along with the IRUL or with the health indicator, you could also embed maybe some textual aid in the output of the AI. Let's, for example, we suspect overheating of this part, for instance. So I think there's multiple ways to get to a better explainability of the models. And on the other question on the maintenance program, well, I believe that's owned by the airline, but it's definitely regulated and approved by the authorities. So to deviate from that, the authorities also need to play a role. And I'm hesitating to volunteer again, David, to say about anything about regulators and that aspect, because I know you have a lot of experience there.
I can follow up on that, add to it kind of thing. Yes, so the operators have their own maintenance program, but it has to be within the regulatory guidelines kind of thing. And currently, we can only do a small percentage, probably 10% of what we could do with CBM because of the regulators. However, we are working on that. There are, my presentation on tomorrow and followed by Dragos, we go into some of those details and what's happening with the regulators and so forth. And then on the artificial intelligence, I want to point out there is a draft memo/report kind of thing from EASA on artificial intelligence. So they are actively working on the program, and basically, I'd say they're not going to approve anything with artificial intelligence affecting your inspection results until at least 2025. And they have, that document basically explains kind of some of the steps for all of that. I would like it sooner, but admittedly, EASA is ahead of the FAA and other regulators. So I am trying to force regulators to the table to talk about all of these things so that we can jointly go forward. So there's that aspect. So we're working slowly on that aspect. And I will say a lot of the times the technical piece is the easy piece to solve. You're based on performance kind of thing. And so so I was going to, with that, I want to hear from the presenters. What do you propose as next? What is next from a technical standpoint? Or is it not technical and more procedural, commercialization kind of thing? What's next?
So if I may just extend on that, so in terms of certifiability and assurance. So at present, most of the PHM is on board. It's not like we are flying an AI algorithm in the airline, in the aircraft itself, which requires higher level of assurance and higher level HIDAL and all those things. So maybe at very next, if you talk about the very next steps, we should concentrate or focus on system and components which are not safety critical and succeed there first. Then, using the results of that success, move to the more safety critical, the equipments which are extremely, we have to be very accurate in our results. And then the third and ultimate step is deploy them on board. So we should go in these baby steps because these are new, very cutting edge technologies. Some of the algorithms, we are still understanding what is going on internally. A deep neural network is a humongous piece of beast. It's thousands of nodes, connections, and which way it is contributing, which way to the end results. We are still trying to figure out those details, how the internals work. So take the baby steps, do the things which is possible now, then incrementally go to the ultimate on-board deployment, real-time alarm to the pilots, and so on and so forth. So I think that would be the most logical step forward here.
That's actually a very good question. What's next? And talking from the structure perspective, and not only, I would say that we are still at the very, very beginning regarding CBM. And especially in structures, we are even in an even lower TRL because many systems are already sensorized. Structures are not. So the way I see future is first to believe that there is potential in CBM and start sensorizing not structures in general, but critical spots maybe that are of interest, spots that we know that are faulty or problematic more frequently than usual in commercial aircrafts, and start gathering data and sharing data. And only then start talking about algorithms, about performance of algorithms and stuff like that. But to me, the takeaway message is start gathering data and share data somehow.
Yeah, if I can add to that, I think the example from Mihaela on the brakes is excellent, because that system is highly redundant. The sensor there is almost directly a health indicator that gets sent to the office already. So for that system to start getting rid of the interval-based inspections and go to CBM, it doesn't need that much of a technology change, and it also doesn't need that much of convincing the regulator that it is a good idea. If you show the results, it's almost a no-brainer to start with this one, right? But why don't we start with that tomorrow? So I would definitely start with that example, and I know it already got a lot of attention from the OEM, so it's probably what is going to happen. But my predecessor said as well, if we start with a very complex AI, then it's going to be a very long and rough road. But if you can start with something simple, then we're probably good for an implementation in hopefully a few years.
It's one question already with many answers, and I still have to add something. So two aspects which I think has to be pursued. So this aspect of getting data from multiple airlines without really getting the data from them, but just using. So I think this will be needed and has to be proven to also show the benefits. But we also need to go, like what you were inferring, Flores, and we have to go back. We will have to go to the manufacturer. So one of the challenges that we have seen in our project is that we are using sensors that were not there to monitor the health of the systems, to try to infer what is the health of the systems. So our car says by 2050, all aircraft will be manufactured for CBM. Maybe we need to start earlier, because then it means that only in 2060 we'll start having CBM. So we need to start earlier to really look at our new future aircraft as being CBM prepared and designed for such approach to reduce costs. Any other? There is a question there from Anthony, then from Derek. I don't know, Derek first.
Yes, hello, Derek Daafschot from Airbus. From this morning, which was very interesting, we've seen a lot on work on damage sensors or health indicators. Will you look for the next steps also towards operational monitoring, like for exceedance monitoring, fatigue monitoring?
So the fatigue monitoring or structure, what Hugh was mentioning. So there is a small nuance on the application domain compared to defense and commercial. Whereas defense, the structure SHM is there, I mean, they're using it. Whereas in commercial, as the impact, structural impact, and those things are not that critical or that frequent. So it also depends on the commercial requirement down the line for structural fatigue management and others, and how it evolves for commercial. So there is also a big difference between whether we are talking about commercial aviation or military aviation, especially in terms of fatigue and structural health monitoring. So we might learn from defense a bit in the context of SHM if we want to do the next steps. So that's just a thought about that, yeah.
Does it mean the answer is no? Or you will not look on operational monitoring in future steps?
Yeah, of course. I mean, it will come if the requirement is more and more. So the reason we don't have sensors in the structure in the commercial aircrafts is that the impacts, structural impact, likely structural impact, and the conditions they're flying might be less hazardous in a way. But if it comes more business critical, I think it will happen. So that's the quick answer that comes to my mind in terms of that. Do you want to add it?
Dirk, do you speak about operational monitoring, and if it's, if I understand well your position?
Yeah, so to the operational monitor, I mean the taking into account the utilization of the aircraft And with that, use this for instance, exceedance loads monitoring to tailor the inspections after an overload event, or also on scheduled maintenance, routine maintenance, to take into account utilization of the aircraft, to lower the maintenance cost in the end for the airline.
Absolutely, this is the way and the idea to go to that direction. If we all agree that, you know, CBM is interesting or viable or economically interesting for structures. And I think it is. I think it absolutely is. Because at least in structures, we rely mainly on NDT, on periodic checks that heavily involve non-destructive testing. What I think we demonstrated in our lab exercises, our intensive lab exercises in ReMAP, is that there is potential. There is the potentiality to sensorize the structures and diagnose, understand the way they degrade, and have early indications on that, and answer all the levels. You can be able to address all levels, even if it's as simple as anomaly detection, so is there or is there not any damage on your structure, as high as the remaining useful life estimation, which is a very, very, allow me to say, a very sexy question, a very sexy item.
Yeah, I think the point is excellent, because honestly, in this project, we've looked mostly into symptoms. So what is the degradation in health, or what is a degradation trend looking like, and didn't look that much into the drivers of degradation. So usage parameters, of course, we have flight hours, cycles, and days, but it would be a very good idea to become a little bit smarter about those usage parameters, yeah. I think we should.
Okay, so Anthony also has a question.
Yeah, Anthony Stillo, American Airlines. Quick question, and I think something that was touched on earlier is the standardization of aircraft parameters and the importance there, specifically when you're partnering with different airlines, putting that data into the same model. Can you elaborate a little bit on how you make the sensor data agnostic to the airline so that the model will behave the same? Because I think that's important as airlines continuously customize those parameter sets. Can you elaborate a little bit on how that, how you see that and taking account for that as more airlines engage in the platform?
Yeah, so
Introduce yourself. Introduce yourself, because you are replacing Miguel.
So my name is Ivan Carrillo. I'm a colleague of Miguel Ángel Esbri, which was presenting earlier the IT platform. So I think the approach of the ReMAP ecosystem is to use this central core, this hub that Miguel was presenting this morning, is in charge of orchestrating a common model, a common catalog of components and parameters and so between the nodes. So the idea is that even if the airlines have the data internally in different formats or so, they all need to map the data using the tools provided by the platform. I don't want to go into much technical detail, but we provide some sort of tools to provide, let's say, a general mapping structure between certain columns of their CSV files into this common catalog of components. So this is the way that we envision to harmonize the data and make sure that, as we said, model builders just need to know beforehand this harmonized catalog of components, and airlines are supposed to to have already the data automatically adapt into this format through the platform.
Yeah. So there's a little bit of work you need to do. You need to tell where's the data, which column is it, what is the unit, what is the sample frequency. So when you configure it, you need to do, as an airline, you need to specify that so that in the background it can all be merged into a standard format.
Do you want? Paul?
Oh, yeah. If I can very, very briefly explain also indeed how we experienced it from KLM, from implementing it. For us, it was very easy to adapt from our data source to how it was configured on the ReMAP node, because the data input files are in a specific KLM format, so to say. And then there's just a conversion matrix that we had to fill in, and then it's automatically in the ReMAP format, so to say, such that it's compatible to all models running on the platform.
I may also add something in parallel, which is the fact that most partners working on developing algorithms for systems, they work with KLM data, except Collins, for obvious reasons, they use their own data from their own clients. But then in the end, with communication between partners, so knowledge was shared but not data. But in the end, colleagues from Collins installing the platform with the platform already running. So maybe you want to share how that was easy. From the perspective of the AI developers, not so much about the airlines.
Yeah, so due to some kind of IP issues and all, we trained our model with the different airlines data. And now we have deployed those models in KLM's platform, and they're running with KLM's 787 fleet. We tested it, it is giving results. We had to take care of some subtle things here and there so that it is reusable, and the aircraft fleet is the same model. But it is possible to use, as long as the aircraft is the same, to train the model with data from one airlines or one entity, and then run those with data from similar aircrafts run by another airlines. In our experience, we saw it is absolutely possible. Of course, we had to talk to each other. Sometimes we had to collect information from each other and use those information, like scaling parameters and other things. But though that generalization ability is possible. It's not that it's not absolutely possible. But given an opportunity as a machine learning person, it might be better to train with the same fleet and test it on the same fleet due to kind of source of variations of coming from routing and other things. So it's always a trade-off. But all these things I expect to be resolved by federated learning, where you train the model data from multiple airlines at the same time, because the model travels to, say, Dubai and Schiphol and all other places, all the airlines hubs, and train the model data from that airlines, and then bring the model and aggregate the model into a final PHM analytics, which is then harnessing the information from all the airlines without the data being fetched into a single location, which is difficult due to jurisdictional and other legal issues. So especially in the aerospace domain, to address that question, this kind of federated learning approach, distributed computing approach is the path forward. And there are a lot of efforts going on, as I understand. University of Amsterdam, Lyon is working on, correct? Yeah. Mark?
Just maybe a complementary question to your explanation, Arta, is it means that the machine learning will adapt to any company, and whether the use of the airlines of the aircraft, whether whatever the operations are, in fact the deep learning will accept the data, and it does not impact, you believe, the models and the results of the model. It means that, because I think Delta is not operating as American airline, neither as KLM, So you think it is neutral for the models?
Yeah, I mean, that is always a risk, like variability in operating conditions. So say Delta is flying within US or US to another route, whereas KLM is flying from Schiphol to another location, and the temperatures and other conditions are different. And that variability will, of course, affect how the model tries to characterize the operating conditions and the behavior of the system. So that is why this federated learning, what I mentioned, is a way forward. So the airlines don't have to share the data among themselves or with the model developers. So they are protecting the privacy of the data. So in the model is just extracting the information that is required. And when the model is extracting all those information that is required, it is also encapsulating all the variations in the operating conditions that you mentioned. So that way, it kind of knows everything about different variations, different routing conditions and all. And that, I think, will solve the problem. But I agree with you. So there is a fundamental problem there. If I train with one route and try to apply in another routing, due to variation I did not see in my training data, the new routing might cause problem in terms of false positives, so to say. Because as those variations were not captured in the training data, those are not part of the nominal operating conditions. So those problems are there. But it also depends on what kind of approach you're taking, whether you're taking a nominal modeling approach, residual model, so to say. You model the healthy conditions, and any deviation from that you try to detect as anomaly or kind of failure happening. Or you have a lot of run to failure data for a given system and train the model with that data. The second example will be more robust because you know that how the degradation evolves over time. You are not considering the healthy operating condition as the baseline for your model. So there are many nuances and subtleties that those come into play. And when developing the models, all those things need to be considered.
Any last question before we close the session? No? Of course, we'll be around, not only us here, but the other colleagues that were also involved in the work. Please engage with us, them, so you can further discuss this. For you here online or physically, you have that chance. Unfortunately, online, please send us the questions if you have questions per email or via Zoom. I suggest that we go then downstairs for the deserved lunch. And I suggest that we come back at the time that was planned. So we have 45 minutes for lunch, and we can start at 1:30 with the panel discussions. So I'll see you downstairs. Thank you very much. Thanks.